All right. I should have not even started. I should have remembered what I was going to do. I would like you, on your pieces of paper, to write down Newton's second law. This is one of those things I know we're going to spend a lot of time on it, and it seems like you need to be able to write it down from this. Okay, let me ask you this question. Can you write more than one version of Newton's law? First clicker question for today then. We have a Newton's second law of motion can be written as. There's 5 of them up here. 4 of them are wrong. Only 1 is correct. Which one is correct? Select the correct one. Do you need more time or is that good? 15 more seconds? More time? All right, 50 seconds. Almost a minute. Do you need more time or is that good? More time? All right, 20 more seconds, but that's it then. You're down to the last 4 seconds. All right. So everybody, usually if they say Newton's second law, they can write F equal to ma, right? Then they say, oh, you know what? A is dv dt, true? And then you can approximate it as the change in v over the change in t, true? So a lot of people will put that like that, okay? Well, is there a form that looks like that? Which one is it? D? Is D the right answer? Or B? Which one? D or B? Dog? Dog or boy? Delta, all right. 64% correct. 64% correct. If you take a look at the postage stamp issued in 1993 in honor of Isaac Newton, you'll see that they have his image. They also have something about light and breaking apart into different spectra of the light and the red, blue, green, blah, blah, blah. But what do they have right here? Is that really a second? I don't see an A in there, but it is, isn't it? And so this is a very convenient form for Newton's second law. How do we interpret MV? Linear momentum. Sometimes they'll use an L, sometimes a P. Often it's a vector with a vector entity on it. This is written in a scalar form, so we could leave that off, but we know it's really velocity is a vector entity, and the force also is a vector entity. And how do we interpret force dt with the time? That's it. Excellent. Impulse. True? That's what impulse is. And in your dynamics textbook, there's typically a whole chapter on force or impulse momentum equations. And so what happens is an impulse contributes to a change in the momentum or linear momentum of the system. An object of mass m is traveling at speed v. It has a linear momentum equal to the product of mv. What is needed to bring the object to rest? Just what term is most closely aligned with what is needed to bring the object to rest? Well, I think we just discussed that. Congratulations. That's a different term, isn't it? Don't you remember that chapter in dynamics, impulse and momentum? Didn't it throw you for a loop at first? It's like, what is going on here? What is going on? What is it? What are we talking about? What is this impulse? True? So that's what it is. There's a bunch of little questions. Hopefully you find them pretty easy. Let me just give them to you. every t seconds, and think of t as like 3 or 5 seconds or 20 milliseconds, some amount of time. Every t seconds, an object of mass m, 2 kilograms, half a kilogram, 0.1 kilogram, traveling at speed v, 30 meters per second, 2 meters per second, whatever, hits a vertical surface and is brought to rest. The surface is stationary. The surface is not moving. It's brought to rest. Under the influence of gravity, the little chunks of mass slide down off the surface and leave room for the next mass behind it to impact it. Boom, boom, boom. Okay? What is needed to keep the surface in place? What, and this is a clicker question, so here's your 30 seconds. What is best to describe what's needed to keep that surface stationary, to keep it in place? Yeah, that vertical blue surface. Isn't it a force that's needed to keep it in place? Let's do this. If no force was applied to it, what would eventually happen to that plate? Would it stay stationary? No. It would start moving. If it was pivoted, it might pivot around this point, or if it's just floating, it would start moving in the x direction because it's being pushed, push, 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 right? Smack, 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 smack. True? So what is needed is a force there. And if the chunks of mass go up in size, they go from small chunks of mass to larger chunks of mass. If the speed of the chunks of mass goes up, wouldn't the force needed to hold it there have to go up? That's true. That's true. All right, continuing this theme. This is an easy question. Maybe I'll just answer it. Nah, I'll let you answer it to recover from that last one. Every t seconds, an object of mass m traveling at speed v hits the vertical surface and is brought to rest, and under the influence of gravity goes down. That's the same thing as what we had before. Write an equation for this physical spacing s between the mass objects. Here are the potential candidates. Is it this, 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 or this? So I'll just give you 30 seconds to answer that question. I just want to know this physical spacing between the mass objects. All right. So what are the SI units for S? It's a distance. It's a physical spacing. Isn't it distance like meters? And what are the units, SI units on velocity? Meters per second. If I multiply that by time in seconds, don't I get a distance? What's the best answer? Isn't B the best answer? Congratulations, there you go. Little higher percentage. Continuing this. Every t seconds, an object, the mass m, traveling at speed v, hits a vertical surface and brought to rest. That's the same statement. What is the mass flow rate of these objects hitting the surface? What is that m dot, that mass flow rate hitting the surface? I'll start it. Well, you might want to use the units to guide you. Isn't this kilograms per second SI units? And isn't this again seconds? Isn't this kilograms? So basically, the mass flow rate, m dot, is, that look best? All right. All right. All right. Now we throw maybe a number or two in here, and maybe you have to have a calculator. Every 33 milliseconds. So that's the time between impacts. It's 0.033 seconds. That's 33 milliseconds. True? A 3 kilogram object traveling at 11 meters per second hits a vertical surface and is brought to rest. The mass then slides off the surface, making room for the next mass. What is the constant force needed to keep the surface in place? What is the constant force needed to keep the surface in place? I'll give you 2 minutes, or is that too much? Or 2 minutes? Well, I think everybody's in, so I'll stop it. Is everybody in? Newton's second law. So maybe you wrote that the force applied, the constant force applied over that time increment is an impulse, and that changes the linear momentum of a particle. And so you just said, let me focus on one particle. Let me focus on one particle. And I know that that one particle is going to come in at mv, linear momentum, smack that wall, and have no more x component of the linear momentum. True? It's just going to fall off. So it's going to be changed by mv. That's the change in the linear momentum. And so if I say, well, that F, and if I say that time, that force has to be applied constantly for one particle over that time period of that particle hitting. So a lot of people probably just said, there, that looks like it. So I have 3 kilograms, and I have 11 meters per second, and I have a 0.033 seconds. True? Kilogram meter per second squared is a Newton. And you ran that number, and what did you get? 1,000. That is very rare. If you give everybody 2 minutes, huh? Is that better? Why do we pick this form? Because it looks like a force is equal to the mass flow rate times the speed, isn't it? And now what's the difference between chunks of mass, discrete chunks of mass, something you're very familiar with coming out of dynamics, and a continuous stream of fluid? Not much. Yeah. So basically, just like what we worked out, that force here, that average force, is the mass of the object, that linear speed, which is going to be brought to rest. So that's the linear momentum of the object striking that plate divided by the time increment between them. That's just mass flow rate times v. So if I had a fluid stream and I knew its velocity impinging on the plate, and I know the mass flow rate, how many kilograms per second, then I could tell you what is the force needed to hold that plate stationary. Isn't it just m dot v? It is. A horizontal water jet of velocity v sub f. So it comes out of this nozzle, which is at rest, but it's coming out at a speed v sub f, hits a vertical flat plate and splashes off the sides. A force of magnitude f is required to hold the cart stationary. What is F? And I got tired of making options. Isn't F equal to m dot v sub f? Yeah. And so there it is. Now we can get lost in mathematics. So now we can say that was a nice, easy transition from dynamics into this linear momentum and fluid streams and fluid mechanics. But didn't we have the RTT? Didn't we develop that very general approach known as the Reynolds transport theorem? Couldn't we apply that equation to mass conservation? Couldn't we apply it to linear momentum? Yes, you can. So what you do is you say, okay, this is the very general system. Here it's applied to the case of linear momentum. So what can change the linear momentum of a system? Force imbalance. Force imbalance. That's what can change it. And how would that change be realized? It could be realized by a transient change in the integral over the control volume. Often this is negligible, or in steady state that term is zero. A lot of times we apply it to steady state problems, so any time derivative is equal to zero. And then what's this? This is how it's flowing out of that control volume. Okay? So it's mathematical, but that's what we have. Now what about this other version? It's still linear momentum, but what did they do? They left this term alone, but what did they do to this term? They broke it into two summations, so the integration over the entire control surface is broken into summations, because often we have a control volume like this, and we have, I'm just going to show one inlet and one outlet. And so if this is the control volume, it flows out here, and it may flow in there. The unit direct normal vector n is in the direction of the outflow, and so when you do the dot product of v dot n, that's positive for the outflow. But when you do the dot product of n dot v for inflow, it's 180 degrees, that's a negative, and you have a negative on the inflows. So what they do is they separate the inflows from the outflows, and they put a plus sign in front of the inflows, I'm sorry, the outflows, and a negative sign in front of the inflows. That's all they did. So instead of going back and computing this integral, you just say that's what the result of that integral is. There's another thing that they've done. They've introduced a beta term. What do you think beta is? Linear momentum correction factor. It's like alpha for kinetic energy correction factor, because we're just going to talk about the average velocity going out and the average velocity, so that's that average over the cross section associated with that mass flow rate coming in and going out. Okay? Now they leave a summation, so you could have a port here and it could go out there, and then they leave one, so you could have inlet here and outlet there, and you could have multiple inlets and multiple outlets. That's great. Often we just have one inlet, one outlet. So let's try and apply that equation. What equation? The generalized linear momentum equation applied to a control volume to solve this problem. This is where normally I would like to just start it. Here we go, let's just go. But I tried to spend, almost 50 minutes talking about a soft introduction and a review of your dynamics material that you've mastered. So here we go. We have a horizontal water jet of velocity v sub f hits a vertical flat plate and splashes off the side. A force of magnitude F is required to hold the cart. What is that force? Well, we already calculated that. That force, here's the answer. Here's the answer, right? F is equal to V sub F times m dot, the mass flow rate. True or false? There's no turbulent flow. It's just splashing off and going. So now let's introduce a control volume. And then let's try to recall the form of that control volume linear momentum equation. So we had sum of all forces acting on that system. Okay, bust that into body forces and surface forces. Okay, body force, the classic body force is gravity with the weight. But we're only going to apply it in the x direction. So is there any weight in the x direction? No, no weight. So there's no body force. Is there any surface forces acting on this control volume? There is, and it's only F. There it is right there. And it's pushing in what direction? The negative x direction. So I need a negative sign in front of it. Okay. We had the time derivative. Well, this is steady state, so that whole time derivative is 0. And then we had the sum over what? Let me move this line over here. We had to sum the beta times m dot times v average over the ins, the sum over all of the outflows, minus the sum over all the ins of the beta m dot v average. True? Wasn't that our equation? Okay, we're only interested in the x direction or x component. I know we have an outflow of mass going this way and that way, cutting across the control volume, but does it have any x component of velocity? The outgoing fluid flow. No, it doesn't. And so the outflow is all 0. And we have beta. Beta is almost always 1. It's a correction factor. In a couple slides, I'll spend more time talking about it. But it's the linear momentum correction factor, which in most cases is close enough to 1. And so what do we have? We have a minus m dot v average. That's all that general Reynolds transport theory applied to linear momentum, boom, brought down and applied. Negative signs cancel on both sides. It's the same answer, isn't it? Okay, we build slowly. We increase the complexity of the problem. So here is the change, that the jet is issuing at the same velocity, at the same mass flow rate coming out of the end of the nozzle, but the cart is moving with the speed toward the nozzle. And you may think, this is kind of a silly application. No, what happens is often we have fluid machinery. What we're doing is we're accelerating fluid flow. We're hitting it, we're diverting it, we're changing its direction. It imparts a force. Maybe it's in a rotating system. It imparts a torque or a moment of the force. And that's how we get fluid flow to generate power out of it to a shaft. And so this, I know, is still pretty abstract and pretty far from the application, but it's getting closer to it. So the question is for the same F and m dot, is F going to be the same if the cart's moving toward the jet? Or is it going to be greater as the cart moves toward the jet at constant speed? Or is it going to be less? Okay, let me make sure I explain this again. Is the cart accelerating or is it just moving at a constant speed? So this problem can't happen forever. It's just happening for a snapshot in time. It's moving at constant speed. Eventually it'll come and smack into the cart or the nozzle and it wouldn't make any sense. But if for a second we have fluid flow issued from a nozzle and you have a little paddle or something here, you could see that the paddle moving away from it would be for a short time period similar to this. Or if the system's moving that way, it would be the paddle would be moving toward it. Okay, so this isn't completely bogus. It does have some. It's getting close to something in reality. Okay, so we had a number of votes. So let me ask everybody to think about this. For the new system meaning it's moving, compared to the original system, which was what? The original system where the cart is stationary. Would this be greater, equal, or less? Answer A, B, or C. You have to almost use your intuition, your experience in solving problems and understanding what we just talked about before to help guide you on this. No, this length right here. Well, you're probably thinking of air entrainment and it's going to slow it down, and I'm not going to have it breaking up and all that, so we're not going to have that. So The speed of it right here crossing that plane is the same v sub f with the same m dot right before it smacks into the cart. All right, so let's see where we're at. Okay, we have a few, but it's going to be larger, isn't it? It's going to be a greater force. Turn it around, maybe do this. Move the cart this way at a constant speed, v equal, the velocity of the cart equal to the speed of the fluid coming out of the nozzle. Are you going to have to apply any force on the cart in that case? No, because it's moving away. It's like it's never going to be smacking into it, right? So as you turn it around and start moving it that way, the new force is going to be multiplied and it's going to be greater. Let's work it out. What would be that new force? Well, you can work it out, and let's just do it slowly. Introduce a control volume, and for that control volume, we say all of our horizontal direction or x direction forces, we only have one. It's the force, and it's in the negative x direction. This is the positive x. It's in the negative x direction. Okay. Forget the transient term in our linear momentum equation. And we're going to have the sum of all the outflows. We only have one outflow. We know that the same mass flow has to, whatever comes in has to go out. So the same mass flow rate for the outflow, okay? Now, that's out of this control volume. But we know it's going out in this direction. It's going out right there. But because the cart's moving, you can have your little vector like this, like that. Okay? So does the fluid flow coming out of this, cutting across the boundary of that control volume right there, does it have any x component of the velocity? Try the other answer. Yes, it does.
Because we've got a surface that the fluid has.
Because the whole cart is moving, and as it comes off of here, it's sliding along, but that cart is moving. So basically it does have, but is it in the positive x or negative x direction for that velocity? It's a negative, and its speed is the velocity of the cart, isn't it? Isn't it? The x component. I'm just focusing on the x component. And the velocity of the cart is 1/2 of v sub f. Okay, that's the outflow. How about the inflow? Well, we have a mass flow rate coming into the control volume. And then what do we have? We have the velocity of the fluid that's cutting across that boundary. But that boundary is moving with the velocity that way. So is the fluid velocity that's cutting across the boundary equal to v sub f, greater than v sub f, or less than v sub f, the speed at which it issues from the nozzle? It's greater. It's catching more. It's catching more. And so isn't that equal to 1 plus 1/2 v sub f? Yes or no? Yeah. So it's equal to 3/2 v sub f. True? Yeah, I need a negative. Thank you. Negative sign on that inflow. True? Now that you have the speeds across it's not a stationary control volume, but it's not accelerating. The control volume is just moving at constant speed v. Now that you have the speeds across the control volume, what are the mass flow rates? Think about the inlet flow rate right here, this mass flow rate right here coming in. Is that equal to the mass flow rate coming out the nozzle? Or is it greater or less? It's going to be slightly more, isn't it? that mass flow, I kind of introduced the mass flow rate that's cutting across the control volume surface, which is the same that's going to be leaving the control volume surface because I'm not accumulating in there. It is going to be greater than the mass flow rate cutting across control volume surfaces, greater than what is going out the nozzle, because the control volume is moving toward the nozzle, moving toward the end of the nozzle. How much greater? Well, look at the equation for m dot. M dot's equal to rho. That didn't change. A, that really didn't change. But what changed? The relative speed. The relative speed. So let me back up here. Can I replace that mass flow rate of the control volume by 1.5 times the mass flow rate coming out of the nozzle? Yes or no? Yeah, that's true, right? All right, so now we look at this equation and let's get rid of a lot of the negative signs. We'll have a 1.5 times the original issuing mass flow rate off of the nozzle times 2 v sub f, true? So 2 times 1.5, 3. Mass flow rate out the nozzle times the velocity issued from the nozzle. So the force for the moving cart is 3 times the original force. Did I do that right? I know you have to be careful. I have to be careful. I made an error. He had to fix it for me. Yes, sir.
It's conceptual that I'm not getting, because I know in reality, if I've got a cart that's moving away from me, I don't have to push it as hard, if at all, to keep it going that way, and that's what's confusing me a bit.
Well, let me ask you to think about it, because what you're doing is you have a fluid stream, like a bunch of little balls coming in, smacking and continuing to smack on it. And if you didn't apply any force here, it would start moving that cart in the direction that the balls are smacking it. So now you're thinking, okay, I got to apply a force to change that linear momentum flow rate of the fluid smacking the cart. And now if I want the cart to go toward the fluid stream, I've got to beef that force up by a factor of 3 if I want to move it at 1/2 the fluid stream toward it. Somebody else have a comment or question? Yes, sir.
Where did the 1.5 come from?
It's capturing more flow rate across the control volume surface than what's coming out of the nozzle, because the cart's moving toward it. And so the mass flow rate coming across that control volume is the rho, that didn't change. The area, that didn't change. But the relative speed going across that control volume boundary.
It's a ratio.
And that relative speed is not the velocity of the nozzle, but it's the velocity of the nozzle plus the velocity of the cart toward the nozzle, which is half of the velocity of the coming out the nozzle. Hence, it's 1 plus 1/2 v sub f. All right, that was a tough problem. You wouldn't think these problems would get that tough that fast, would you? All right, let's go and do this. Let's analyze a cart that is stationary, it's not moving, and it has a vane on it that deflects the fluid flow. So we have a stationary nozzle that issues at v sub f, a stationary cart that's sitting there, and it deflects or diverts with this plate, and it diverts the fluid by an angle of 30 degrees. Okay? Now, the cart has a weight on it, so let's include the 200 Newton weight, and ask the question, calculate the horizontal force to keep the cart there, and then calculate the vertical force to keep the cart there, stationary. So, how would you solve this problem? Using the tools this chapter, introduce a control volume, and then apply our balance of linear momentum. Some people would say conservation of linear momentum, but the sum of the forces can increase or decrease the linear momentum. I wouldn't quibble with them to say you're wrong, but I personally would stay away from conservation of linear momentum. Energy is conserved, but linear momentum is not. Okay, so there's our control volume. If you like, you can cut it right here so it's perpendicular to the flow, which is great. That's fine. And let's go ahead and apply. So in x direction, I have no body force and only a negative v sub h surface force. I don't worry about the transient term. Take that out, okay, 0. But I have the sum over all of the outflows. There's only one outflow. It's over here. And that's going to be the beta, forget it, it's 1, times the mass flow rate going out, times the v sub x. That's our x component of the speed going out. Okay. Minus the mass flow rate coming in, v sub x coming in. Well, let's take a look at the in x component. If this is not moving, the jet's not breaking up, it's staying consistent, then isn't that v sub f? V sub x is equal to v sub f. This is what v sub f is. It's coming out of this stationary nozzle. So the flow rate coming in right here is, the average speed is v sub f? Yes or no?
Yes.
Good. All right. Is this m dot the same as that m dot? It is. All right. How about this v sub x? Is that v sub f times cosine of 30 degrees, or let's put phi or theta or some symbol for, because I'm leaving symbols there, phi. Okay. So f of h is equal to the mass flow rate times v sub f times 1 minus the cosine of phi. True or false? Did I do the math okay? And then we could substitute numbers. We could substitute, okay, it's 30 kilograms per second, 35 meters per second, cosine of 30 degrees. We could calculate that. Let's do it now in the y direction. Well, you have the same control volume. And now I'm going to have what two forces act in the y direction. And yes, this is positive x direction, positive y direction. Okay. So I have a positive f of v acting upward. Is that a body or a surface force? Surface. Minus w acting, well, w acting downward. Is that a body force or a surface force? Body force. That's following the terminology in the textbook and used in a lot of fluid mechanics applications and literature. All right. Equal to, forget the transient term, it's steady state. All right. Now we're going to have a plus the mass flow rate times the outflow component. So what is the v in the y? It'll be v sub f times the sine of the angle 30 degrees. Isn't that our out? And then how about the in? Minus m dot times 0. Excellent. True? Did we do that one okay? So now we can read this equation. V sub f is equal to the weight of the cart plus the mass flow rate times its v, that's like linear momentum flow rate, but it comes in with 0 and it has to go out with the positive sine phi times that, m dot v. It deflected the stream upward. In order to deflect the stream upward, the stream is kind of pushing the cart down, meeting the reaction force to keep it stationary. It has to go increase. It increases by this amount right there. True? All right. Well, what do you think we like to do as engineers if we got a little deflector cart? Hey, this is what happens at 30 degrees. I wonder what happens at 45 degrees. I wonder what happens at 90 degrees. That was what we were just studying, wasn't it? At 90 degrees. So think about a bunch of carts on a surface. I'll miniaturize the carts. Here's the cart. And it has another cart here, and another cart here, and another cart here, and another cart here. So we have 5 carts, and we're interested in comparing the force horizontal from the first cart and the force vertical the first cart, force vertical second cart, force horizontal second cart, force vertical third cart, force horizontal third cart, force horizontal fourth cart, horizontal fifth cart, vertical fourth cart, vertical fifth cart. Okay. And what we're going to do is we're going to have deflector plates. This deflector plate that we had right here deflected at some angle, some theta. That's the one that we just analyzed. Okay? So the fluid flow is coming in and it's being deflected and it goes out that way. Okay. Somebody says, that's really steep in that deflector cart. The deflector on the cart comes in horizontal, leaves vertical. Somebody else says, keep going, you can do better. It comes in and it leaves. Ed, what do you think the most extreme might be? It comes in and it leaves like that. And then what's the other least extreme? Like, forget it. Is that really a deflector cart? Yeah, here's your kind of starting deflector cart. No deflection, right? Okay. Which one do you think, we want to compare all 5 of these. Do you want to compare the horizontal or vertical first? The horizontal, okay. FH1, FH2, FH3, FH4, and FH5. The question, I'll ask a clicker question, is FH1 greater than, equal to, or less than FH2? FH1, is it greater than, less than, or equal to FH2? So I back up a little bit. One of the ways to look at it is, can you tell what the magnitude of FH1 would be? No, it's horizontal, not vertical, no weight, right? So it's 0. So, and then as it deflects the FH2 is going to have to be larger and larger and larger. So what's the right answer? C. Isn't C? C's the right answer. All right, let's do this one. So it goes like this. How about 2 and 3, non-clicker question, just 2 and 3. Is that trend good? How about 3 to 4? Okay, clicker question. It'll be, come on now. Greater than, equal to, or less than A, B, or C. Let's start that. Compare 3 with FH4. So you're deflecting in 4. 3 deflects it straight up. 4 deflects it back on itself some. Yeah, see how the fluid comes in and then it gets deflected in 4. In 3 it's straight up, it deflected straight up. All right. So let's just look at the results. Why is it that result? I mean, so how about this? Maybe I should have done this. Can somebody tell me what FH5 is? It's a magnitude, it's a calculation. No, FH5. you do a control volume around this cart. You have an inflow, which makes this F of H5, if you only had the inflow and you diverted it out like this would be FH3 would be the mass flow rate of the fluid hitting the cart and that velocity coming in, and then you divert it up. True? We worked that out. It's m dot v, m dot v. We've done that a couple times. Okay. Here, you're going to have an out. What is the direction of the out? Yeah, I'm running maybe, well, I think I may have enough time to do that in more detail, looking at the clock. Yes, sir.
Where is it coming from?
Because it's coming in and then it's going out. Okay, let's do this one. Let's go back. You do your control volume right here. We had a negative F on the force balance, and we had over on the other side and no outflow, 0 for the outflow, but we had a negative m dot v sub f for the inflow, true? And then we got rid of that, and we said F is equal to m dot v. Great. Let's do the same thing here. So we're going to have negative FH of 5, that's in the negative pushing back on the cart. Okay, equal to, what about the outflow? The outflow is m dot v, but the v is not in the positive x direction, it's in the negative x direction. True? And then what about the inflow? It was m dot v in the positive x direction. So each term has a negative in front of it, and v sub h5 is equal to 2m dot v. I know I'm writing small, I'm trying to cover a lot of ground here, but if you get the big road map, you'll see, oh yeah, let the vein that's trying to catch that fluid really change the direction of the fluid. Hence, I have a strong force at that end of that rotating machinery. I get a strong torque, get a lot of power out of that fluid stream. All right, now, I don't say this is easier, but let's work through it. FV1, FV2, FV3, FV4, FV5. These are the vertical forces. Professor, does the cart have weight? Yes, it does. Can you tell me what FV1 has to be? It's W, because it has weight. It has weight, W. Okay, so this is equal to weight. Just like the first case, we said, oh yeah, FH1 is 0, FV1 is equal to the weight of the cart. True? Okay, now, time to redeem ourselves. Another clicker question. FV1, is it greater than, equal to, or less than FV2? A, B, or C? The force, vertical, to hold that cart up. How does it change as the deflector plate comes into play? All right. What do you think? We're going to get a lot of right answers. So it's going to have a greater vertical force. So it's C. True? Is that true? 72%. Okay. Now, what about FV2 versus FV3? I'll just out loud. Which one's greater? FV3? FV3. Right. All right. Now, I'm going to go slow, and I'm going to ask this question. The relationship between V3 and V4. So let's say answer either A, answer B, or answer C. All right. So in this case, it is A, and what happens is it's if you want the maximum downward force that the cart pushes on the ground, hence the ground has to push back up onto the cart. So you want a large VF coming up. Then try to get the fluid to be diverted and have a large Y component of the momentum going upward. And it's gone down. It was greater here and less there. Yeah. So you say, all right, now what about this one, the very, very last 5? It doesn't have any Y component coming in. Does it have any Y component going out, the fluid stream? Oh, you want to do a clicker? Nah, come on now. And guess what it's equal to? FV1. It's equal to the weight of the cart. Now, somebody says, I better have a strong device there because it probably the top and the bottom will want to pull apart and break. If it would break, it'd probably want to break somewhere right in the middle, wouldn't it? Because it's trying to turn it and then turn it again. So internal forces, but we're not interested in those internal forces. I just thought of an application problem. Insert new page. How many people have been on aircraft? Ever flown an aircraft? Yeah. Anybody ever sit out there and look out the wing and watch especially the jet engine? What happens? What happens when the pilot lands? Do the brakes, like on our car, the tires, do they provide the majority of the braking in the aircraft? No, they don't. The tires don't. Flaps go up. But what happens also at the back of the engine and then the airplane pilot gives it more fuel? Reverse thrust. And so who has an image of what's going on when that happens in their mind? You don't recall seeing that? So the jet engine is like this, and then some piece of equipment detaches, and I forget where it starts, and it goes together. Maybe it's like this, and then they move and they pinch. They pinch in the middle, and so the gases come this way, they hit a roadblock, and they're forced that way. Remember? Did you see that? Right? Say, don't buy your ticket in first class. Say, I'll sit in the back of the aircraft where I can look at the back of the engines. I have to study this. Right? So give your ticket in first class to some other person, you know. But that's what's happening. The same thing. It's so it's throwing it back. It's a reverse thrust. All right, done with that. I have skipped this problem. What about this linear momentum correction factor, the symbol beta? Well, this is pretty straightforward. What we want is think about flow in a duct or a pipe. It's easiest to do it thinking about at a pipe that's round, and then you have a round pipe in the center line right there. What we like to do is we know that the velocity profile is something where it's typically the fastest in the middle and no slip. It goes to zero speed at the walls of the pipe, true? Or the walls of the duct. And we know that a little ring, if I just looked at it, this little area of constant speed right in here, it would be a little ring of fluid coming through that little red ring. Okay, it all has the same speed. And as the ring gets larger, the speed will go down until the ring gets to the radius, and then the speed is zero. And if the ring is really small, it'll be the highest speed. Okay, now, so if I wanted to calculate the linear momentum flow rate through some section of the pipe right here, what I would do is I'd say, well, I'm going to have to do a summation over all these little area rings of what? Well, I'd have to do the density times the velocity. That gives me the mass flow rate in that ring. Mass flow rate in that ring. And then multiply it by V to get the linear momentum flow rate in that ring, and then sum up over all of the area for all the rings. Well, that's too complicated. What we want to do is we want to use a simple equation. We want to use an equation that says, give me the average speed in the pipe. It's not the maximum. It's not the minimum. It's some average speed. You know, we know how to calculate that average speed. We already did that before. It's 1 over the area, the integral of V dA. True or false? That's true. That's our equation to calculate the average speed. I would like to use my average speed multiplied by the mass flow rate down the pipe, and that would be my linear momentum flow rate. But when you put in a real velocity profile, that equation doesn't work. So to make it work, you introduce a correction factor. You introduce beta, the linear momentum correction factor. So the equation for beta is the integral over the area of rho v squared dA. And then you divide by the mass flow rate. Okay, well, what was our equation for the mass flow rate? Rho A V average, isn't it? Rho A V average. So you divide by rho A V average squared. Where is it? Well, you get a V average there and a V average there, so it's V average squared. Density, the same, incompressible, negligible density. And so then what you have is you have the 1 over the area, the integral over the area of the velocity divided by the average velocity squared. And that's the equation for the beta, the linear momentum correction factor. Professor, it's been a long time since I've been in calculus, and I'm itching. In mechanical engineering, it's just plus and minus, plus and minus. Sometimes we use a hyperbolic, this and that. I need to do some integration. Here you go. Let's do some integration. So they say, here is my analytic expression for the velocity profile for flow in a pipe. So that's U is equal to U max times 1 minus R over cap R to the 1/7 power. Determine the average fluid speed, U average. Well, what is U average? The average fluid speed. Isn't that 1 over the area, the integral of the U, which is the product of U max, times 1 minus R over cap R to the 1/7 power, times dA. And we're going to integrate with little rings, 2 pi R dr, R going from 0 to R going to cap R. I don't want to leave you in the dust, but is that right? Does that look familiar? Okay. So we can take the U max out, and then we can recall what is that area. That area is pi cap R squared, true? Is that true? And so we have 1 minus lowercase r over cap R to the 1/7 power 2 pi lowercase r dr going from 0 to cap R. Did I do okay? So look at, this is cap R, lowercase r over cap R. This is lowercase r over cap R. This is d lowercase r over cap R. So introduce the variable x. So I integrate 1 minus x to the 1/7. Oh, the pi's cancel, don't they? Times 2 times x dx. Now x goes from 0 to 1. So for this problem, all I have to do is compute this integral. See, you've been waiting. All that calculus I learned, I need to use it, right? Well, how would I solve that problem? Maybe 20 years ago I'd said, give me the calculus book and I'll look it up and I'll try and do it myself by hand. But otherwise, so in Wolfram Alpha, type integrate, type in your equation, and say from 0 to 1. And you have to wait. That's the hardest part, for about a millisecond. And it spits it back out and says, is that what you intended? Yep, that's exactly what I intended. Here's your answer. 49 over 60, which is approximately 82%. So what do we interpret? We say, hey, U average is 82% of the maximum. True? We finished part A for that problem. You ready to move to part B, which is the kinetic energy correction factor? And then part C, the linear momentum correction factor? All right, bear with me, please. We'll go ahead and do it. Let me erase a little space right here. Put a line in. And I'm only going to do one of these. Which one do you want to do, the kinetic energy or the linear momentum? I'll take a vote on that. B or C? Part B or part C? C? Okay. So what was our equation for beta? 1 over area, the integral of U over, what was it? The integral of U over U average squared dA, true or false? And you're going to have to remember that U average is equal to 49, was it 49 over 60? I can't remember.
Yeah,
49 over 60, yeah, times U max. We're going to have to use that. Okay, so now we integrate 1 over pi r squared, integral 0 to cap r, put in U, it's U max, times 1 minus r over cap r to the 1/7 power, divided by U average, which was 49 over 60 U max. All of that squared times 2 pi r dr. I almost have enough room to write it all out. We cancel the pi's. We'll bring that cap r squared under there and under there. We'll introduce x is equal to r over cap r as a new variable of integration. And now we find that beta is equal to the integral from 0 to 1. Oh, the U maxes cancel, don't they? Yep, thank you. Yeah, that's good. 1 minus x to the 1/7 times 60 over 49 squared times 2x dx. I look at that. What do you think I do? I'll get my calculus book, or I'll do it on with the little assistance from Wolfram Alpha. Well, here it is for alpha. Here it is for the beta. So did I input the equation correctly? You type integrate the equation where x is the variable from 0 to 1. It looks like this is the right equation. The answer is 50 over 49, which is 1.0204. So for that velocity profile, the linear momentum correction factor, beta, is very, very close to 1. As a homework assignment, there it is for alpha. You can check yourself. All right. Should I call it a day, or should we solve another problem? All right. Thank you very much.